Hello students, in this session we shall discuss a few derivations from the chapter 11 three-dimensional geometry. First derivation, equation of a line through a given point and parallel to a given vector. So we need a fixed point and a line which passes through that fixed point. We need a vector which is parallel to this line. So let's take point A to be the fixed point. Let OA vector, represented as A vector, be its position vector. Let L be the line which passes through the point A, and let vector B be the vector which is parallel to this line. Let's take an arbitrary point P on the line L and let its position vector be equal to R vector. Observe that AP vector is parallel to vector B. In other words, they are collinear vectors. And if vector A and vector B are collinear, then A can be written as lambda times vector B. So here vector AP is parallel to vector B, so we can write AP vector is equal to lambda times B vector, where lambda is some real number. Now, we know that AP vector can be written as OP vector minus OA vector. Substituting all the information that we know, AP vector is lambda into B vector, OP vector is R vector, and OA vector is A vector. So we get lambda times vector B is equal to vector R minus vector A. Rearranging, we get vector R is equal to vector A plus lambda times vector B. And this is called the vector equation of the line. Now let's derive the Cartesian form of the equation. Let the fixed point be x1, y1, z1. So OA vector will be x1 I cap plus y1 j cap plus z1 k cap. Let the arbitrary point P be x, y, z. So vector R will be xi cap plus yj cap plus zk cap. Let A, B and C be the direction ratios of the parallel vector. So we get vector B is equal to AI cap plus BJ cap plus CK cap. Now substituting all this information in the vector form of the equation, we get xi cap plus yj cap plus zk cap is equal to x1 I cap plus y1 j cap plus z1 k cap plus lambda times A I cap plus B j cap plus C k cap. Next step, let's equate the terms. Now you see, two vectors are equal to each other, so their corresponding elements are equal. So we can write x is equal to x1 plus lambda times A. Y is equal to y1 plus lambda times B. Z is equal to z1 plus lambda times C. So we get this step. Now we observe that x minus x1 divided by A is equal to lambda. Y minus y1 divided by B is equal to lambda. And z minus z1 divided by C is equal to lambda. Now eliminating this lambda, we get x minus x1 by A plus y minus y1 by B is equal to z minus z1 by C. Now, where A, B and C are the direction ratios of the parallel line. Now, suppose L, M and N, the direction cosines are given to us, then the equation will be x minus x1 by L equal to y minus y1 by M equal to z minus z1 by N. This is the required Cartesian form. Next derivation, equation of a line passing through two given points. So let's take 2 points, A and B, and let vector A be the position vector of the point A and vector B be the position vector of the point B. Now let us consider an arbitrary point P on this line with the position vector, vector R. Now observe that vector AP and vector AB are collinear vectors. So, we can write one vector as lambda times the other vector. Hence, we get AP vector is lambda times vector AB, where lambda is any real number. AP vector can be written as OP minus OA, and AB vector can be written as OB minus OA. Hence, we get this step. Substituting OP vector as R vector, OA vector as A vector, OB vector as B vector, we get vector R minus vector A is equal to lambda times vector B minus vector A. Rearranging, we get vector R is equal to vector A plus lambda times vector B minus vector A. And this is called the vector equation of the required line. Now to derive the Cartesian form, from the point A, that is x1, y1, z1, we can write vector A as x1 I cap plus y1 j cap plus z1 k cap. Vector B can be written as x2 I cap plus y2 j cap plus z2 k cap. And vector R can be written as xi cap plus yj cap plus zk cap. Now substituting all this in the vector equation, we get this step. Now observe here, we have x2 I cap plus y2 j cap plus z2 k cap minus x1 I cap plus y1 j cap plus z1 k cap. So subtracting this, we get the next step. This is same, this is same. Here we get x2 minus x1 into I cap, y2 minus y1 into j cap plus z2 minus z1 into k cap. Now we see that two vectors are equal to each other, so their corresponding entries have to be equal. So let's equate the like terms. So equating the coefficients of I cap, j cap and k cap, we get x is equal to x1 plus lambda times x2 minus x1. Y is equal to y1 plus lambda times y2 minus y1. Z is equal to Z1 plus lambda times Z2 minus Z1. Now, from here, we get x minus x1 divided by x2 minus x1 is equal to lambda. Y minus y1 divided by y2 minus y1 is equal to lambda. And z minus z1 divided by z2 minus z1 is equal to lambda. Eliminating the term lambda, we get x minus x1 divided by x2 minus x1 is equal to y minus y1 divided by y2 minus y1 equal to z minus z1 divided by z2 minus z1. And this is the Cartesian form of the required equation. Now let's find the angle between two lines. Suppose L1 and L2 be the two lines passing through the origin with direction ratios A1, B1, C1 and A2, B2, C2 respectively. Let theta be the angle between them. Let P and Q be points on L1 and L2 respectively. So now, since the direction ratios of L1 are A1, B1, C1 and a point P lies on L1, OP vector, the position vector of P, can be given by A1 I cap plus B1 J cap plus C1 K cap. Similarly, since Q is the point on L2 and A2, B2, C2 are its direction ratios, we can write OQ vector, that is the position vector of Q, as A2 I cap plus B2 J cap plus C2 K cap. Hence we get the two vectors, vector A and vector B. Now we know that the dot product of two vectors, vector A dot vector B, is given by magnitude of vector A into magnitude of vector B into cos theta. Now we have to find the value of this theta. So rearranging this, we get cos theta is equal to vector A dot vector B divided by magnitude of vector A into magnitude of vector B. Now vector B, A and vector B are given in component form. So their dot product will be A1 into A2 plus B1 into B2 plus C1 into C2 divided by magnitude of A is given by square root of A1 square plus B1 square plus C1 square, and magnitude of B is given by A2 square plus B2 square plus C2 square. This is how we find the value of theta, that is the angle between the two lines. Skew lines. There are lines in space which are neither intersecting nor parallel, and also they are non-coplanar. Such lines are called as skew lines. For example, imagine a line on the ceiling. Suppose this is the ceiling, I'll take it as plane 1, and this is the floor. So this is plane 2. Imagine a line over here like this. So let's take this as L1. And let's imagine another line like this. Let's take it as L2. You observe that these two lines, L1 and L2, never intersect. They are not intersecting. Also, they are not parallel. And also, since they are lying on two different planes, they are non-coplanar. So this is an example. These lines are the examples for skew lines. Other examples, if I have to give, observe the line AB and CD. They are on completely different planes. They are not parallel to each other, and also they never intersect. So AB and CD are also an example for the skew lines. Now, suppose I had taken parallel lines. So observe if I take this line, I'll call it as EF. You observe that if you consider the two parallel lines, then you can always draw a plane. So you can draw the other set of parallel lines and you'll get a plane. So it becomes planar, not non-coplanar. They will be coplanar. Okay, so parallel lines will not form skew lines. If I have to explain it one more time, suppose I take two parallel lines like this. Now, now if you see like this, they are in different planes. But what happens if you draw the other set of parallel lines? You'll get a plane and you see that your L1 and L2 will lie on the same plane. So it becomes coplanar and hence these lines L1 and L2 will not be skew lines. So therefore it is necessary to consider not parallel, not intersecting and non-coplanar. Only such lines are called as the skew lines. Let us now derive the equation to find the distance between two skew lines. Let's take line 1 and line 2 to be two skew lines in space. We know that the distance between these, that is, the shortest distance between these two lines is the perpendicular distance between them. And if you observe carefully, the perpendicular distance between L1 and L2 will be same as the shortest distance between the two planes. With this idea, let us proceed to find the equation. Let's take L1 and L2 be two skew lines. Let B1 vector and B2 vector be parallel to L1 and L2 respectively. Now suppose I take S and T on L1 and L2 respectively. We get a distance, but definitely this is not the shortest distance because this is not a perpendicular distance. So let's take the position vector of S as A1 vector, position vector of T as A2 vector. Now, as I said earlier, the shortest distance is the perpendicular distance between L1 and L2. So let PQ be the shortest distance between L1 and L2. Observe that PQ is perpendicular to L1 and also PQ is perpendicular to L2. But B1 vector is parallel to L1 vector. So this PQ has to be perpendicular with B1 also, and PQ is perpendicular to B2 vector because L2 and B2 are parallel. Hence we get vector PQ is perpendicular to B1 and vector PQ is perpendicular to B2. So clearly the vector PQ has to be B1 vector cross B2 vector because we know that only the cross product will be perpendicular to both the vectors B1 vector and B2 vector. So vector PQ has to be equal to B1 vector cross B2 vector. Now observe this picture carefully. The black line is L1, the red line is L2. The yellow line is the perpendicular distance PQ. And as we discussed earlier, this perpendicular distance between the lines L1 and L2 is nothing but the distance between these two planes. So this yellow line is equal to this blue line. Now if you see the light blue line here, this is nothing but ST. Observe that this line, which is equal to PQ, is the projection of ST. So, now using the formula for projection, we get PQ is equal to ST vector dot PQ vector divided by magnitude of PQ vector. PQ vector, we already know, it is B1 vector cross B2 vector. ST vector can be written as OT vector minus OS vector. So OT vector is nothing but A2 vector and OS vector is nothing but A1 vector. So substituting, we get A2 vector minus A1 vector dot B1 vector cross B2 vector divided by magnitude of PQ will be magnitude of B1 vector cross B2 vector. To derive the Cartesian form, let's take the vector A1 to be x1 I cap plus y1 j cap plus z1 k cap, A2 vector be x2 I cap plus y2 j cap plus z2 k cap, vector B1 is equal to A1 I cap plus B1 j cap plus C1 k cap, and vector B2 is equal to A2 I cap plus B2 j cap plus C2 k cap. Now substituting in the vector form, that is A2 vector minus A1 vector dot product with B1 vector cross B2 vector divided by magnitude of B1 vector cross B2 vector. So the numerator, if you see, this is nothing but the scalar triple product. And the scalar triple product, that is A dot B cross C, can be found out as the determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3, which are nothing but the direction ratios of vector A, vector B, and vector C. So the numerator can be written as the coefficients or the direction ratios of A2 minus A1, B1 and B2 vector. So the direction ratios of A2 minus A1 are x2 minus x1, y2 minus y1 and z2 minus z1. Direction ratios of B1 are A1, B1, C1. Direction ratios of B2 are A2, B2, C2. Hence we get the numerator. In the denominator, we have to find the magnitude of B1 vector cross B2 vector. So we have B1 vector cross B2 vector is nothing but the determinant I, J, K. B1 vector components are A1, B1, C1, A2, B2 and C2 are the components of vector B2. So the cross product will be equal to I cap into B1 C2 minus C1 B2 minus J cap into A1 C2 minus C1 A2 plus K cap into A1 B2 minus B1 A2. Now, taking the magnitude of this B1 vector cross B2 vector, we get square root of B1 C1 minus C1, B1 C2 minus C1 B2 the whole square plus A1 C2 minus C1 A2 the whole square plus A1 B2 minus B1 A2 the whole square. And this is nothing but our denominator. So the shortest distance between two skew lines in Cartesian form is given by this formula. Let us now derive the distance between two parallel lines. Let L1 and L2 be two parallel lines. Let B vector be another parallel vector. Let S and T be the points on L1 and L2 with position vectors A1 vector and A2 vector respectively as given in the figure. Now distance between these two parallel lines will be the perpendicular distance between them. So let's take PT to be the shortest distance between L1 and L2. Now observe that PST forms a right angled triangle. Let's take the angle between SP and ST as theta. So the angle between vector B and vector ST will be equal to theta. Now from the triangle, sine theta will be opposite by hypotenuse, that is PT by ST. So we get PT, that is the distance, is equal to ST into sine theta. Now we have the cross product of vector B cross vector ST is equal to magnitude of vector B into magnitude of vector ST sine theta into n cap. Now observe that ST sine theta is nothing but PT. So from the equation 1, we can substitute ST sine theta as PT. Now, distance is a scalar quantity, but we have two vectors here which are equal to each other. So, in order to find the distance PT, we will take the magnitude. So, magnitude of B vector cross ST vector will be equal to magnitude of vector B, which is a scalar. PT is the distance required, and magnitude of n cap will be equal to 1. So rearranging, we get PT is equal to magnitude of vector B cross vector ST divided by magnitude of vector B. Now, ST vector can be written as A2 vector minus A1 vector. Hence, we have the shortest distance between two parallel lines is equal to magnitude of vector B cross vector A2 minus vector A1 divided by magnitude of vector B.